Bismillah ar-Rahman ar-Rahim. Dear students, this is the course of instrumental chemistry, experiment ion selective electrode. Ion selective electrode is one of the electrochemistry experiments, electrochemistry that measured potential. Ion selective electrode is an analytical technique used to determine the concentration of ions in aqueous solution by measuring the potential. An example of ion selective electrode, the pH meter, which used to measure the amount of H3O plus or the acidity of the solution. Ion selective electrode can measure the concentration of certain ion in solution without being affected by other ions without interference. This is done by using a selective membrane at the ion selective electrode, which only allows the desired ion to pass and excluded the passage of other ions. In this experiment, the example is fluoride ion selective electrode. Ion selective electrode for fluoride contain a crystal of lanthanum fluoride as the membrane, through which fluoride ions are mobile. Within ion selective electrode, there is an internal reference electrode made of silver wire coated with solid silver chloride embedded in saturated potassium chloride filling solution. This is the ion selective electrode part. The other part should be reference electrode. When they are immersed in aqueous solution that containing fluoride, potential develops and measured using pH meter. The potential developed at equilibrium, which is the potential difference between reference electrode and ion selective electrode, can be described by Nernst equation. Nernst equation says the potential, the measured electrode potential, equal to E naught, standard electrode potential, plus RT over NF, R gas constant, T temperature in Kelvin, N number of charges or number of electrons, F Faraday constants, multiplied by ln activity. These values measured using pH meter. Nernst equation in its original form relate the potential with the activity which is the active concentration. It is a theoretical type of concentration. Nernst equation is an equation of linearity. If you plot at y-axis potential and linear activity at x-axis, the relationship is linear, with the E naught, the intercept with y-axis, and the slope equal to RT over NF. The concentration used in Nernst equation is activity, which is the effective concentration, not molarity, which is the total fluoride ion concentration, which may include some bond ions. The electrode respond only to free ions, so it's important to avoid the formation of complexes that would lower the activity and therefore electrode response. If you need to relate potential with concentration, molarity concentration, the ionic strength should be kept constant, activity and molarity proportional. If the ionic strength is constant, so the activity coefficient is constant. Activity equal activity coefficient multiplied by the concentration. If the activity coefficient is kept constant, you can use molarity concentration instead of activity in Nernst equation. The ionic strength that keep the activity coefficient constant is related to the charge and concentration of each species ions in the solution. Ionic strength I equal to half the summation of concentration multiplied by the square charge of each species in the solution. Addition of high concentration of non-interfering ions in the buffer using buffer solution keeps the total ionic strength constant and prevents fluctuation in the activity coefficient, and in this case you can use the molarity concentration instead of the activity. Besides, you can use the constants of R, temperature, N, and Faraday to identify these parameters in Nernst equation. In fluoride ion selective electrode, N equal -1 minus electron, temperature 25 Celsius, which is converted to Kelvin. Faraday and R constant are constants, so the final form of Nernst equation could be potential equals standard potential minus 59.2 millivolt logarithm concentration as molarity concentration. This equation now is expressed by molarity concentration instead of activity. This is a special case when the ionic strength is kept constant and consequently the activity coefficient is kept constant. In this case, you can use molarity concentration instead of activity. Besides, we convert ln to logarithm, the relationship expressed in ln to logarithm using the constant 2.303 mathematically. The final form of Nernst equation became E equal E naught minus 59.2 millivolt logarithm molarity. For fluoride ion selective electrode, the interfering ion is hydroxide ion. Hydroxide can interfere with the measurement of fluoride. To avoid this interfering expectation, we again use a buffered solution. But the buffer solution now serve as ionic strength buffer, keep the ionic strength constant, and consequently keep the activity coefficient constant from one side. From the other side, to prevent the hydroxide ion from interfering with fluoride analysis. Nernst equation in this case is a linear relationship. If you plot potential on y-axis and logarithm molarity on the x-axis, you get a linear straight line descending because the slope is negative minus 59.2. We can draw a calibration curve between the concentration of known solutions measuring the potential. The calibration curve can be used to know the concentration of any unknown fluoride solution. Fluoride ion is good at low concentration, but at high concentration, it is danger at high concentration. Determination of the amount of fluoride in any sample can be done using two different methods: standard addition method and calibration curve method. Calibration curve method, several fluoride solutions with a known concentration can be prepared and measure the potential, plot the potential versus logarithm concentration, and from this plot you can determine the concentration of any unknown fluoride solution, and you can measure the slope